In this video, we'll solve the single slope PEB structure project. Firstly, let's open our MkaPEB software. If the software interface is in Turkish, you can select the language from the language setting option. Let's start by creating a new project and open the new project. Let's start by creating a new project and open the new project. Let our truss length be 20 meters, column height is 8 meters and axis spacing is 6 meters. Firstly, let's fix our truss attributes from Edit Truss window. The tapered region will continue along the two purlins at the corners. The column edge height at the corner is 0.80 meters or 1 meters if possible. It is a roof that doesn't have much slope, it has a slope of 6 to 7%. Let's update our structural model by pressing Apply Changes. There are many loading codes in MkaPEB. I assume this project will be done in India, therefore I choose IS 875 as the loading code. There are sandwich panel as cladding on the roof. It is possible to define from this section, to choose whether there is a solar panel on our roof or not. But we will not use solar panels in this project. Let's define a snow load of around 10 to 15 kilograms per square meter, considering the rain load. Let's select wind speed as 44 meters per second, and is not consider internal pressure coefficients. Our building is inside the city, so choose terrain category 4. I close it by pressing the OK button. Let's move on to earthquake code automatically comes as is 1893. Our building is located in an earthquake-free area in Chennai, India. The building importance class is 3, because of our building is standard building. Let our soil class be a poor soil, I choose ground type C soft soils. Let's move on to the secondary elements. The program includes many structural steel design codes. Turkish, American, Indian, Saudi Arabia, Eurocode 3. I assume our building is in India, we have to use as 800. I try to choose as roof purlins as light as possible. The loads action on roof is so small. I can define C200 to 15 profile as purlin section, 4.87 kilograms per meter. We can use sag rods, there is no change due to low roof slope. Let's move on to wall girts. I want to use the same wall girts on the right and left of the building. So I marked all have same properties. C200 to 15 section seems to be sufficient here too. Let's see if there is a smaller section. If I can increase girt count to 7, it will be C150 to 15 profile, 3.70 kilograms. The other axis of the building, there is no problem either, it works 90% of capacity. Let's make our building a little bigger then. Our building width is 60 meters. Main columns, right and left columns. 140 by 10 over there. These profiles are not currently in the database, so I'm adding them myself. 400 by 8 We have chosen the starting section of this column here. The cross-section higher at the upper end of the column will come from the truss properties. Now we come to the beam section. I will use the same profile in the beam section. There is a problem at Girts. The program says that as the width of the building has increased and the wind loads on the girts have changed. 150 to 20 or 200 to 15, which is better? This one looks lighter. I looked at the other side. I'm replacing it with the same cross section, I've replaced it with 200 to 15. We have a capacity of 58% in the columns we have chosen. I think these are the column sections 14 and 15. In the beams, I have chosen a little too large sections. We can shrink them a little. Maybe 300 versions, not 400. Main columns, I'd use them not 400 to 10, but 300 this time. Even thinner. In S235 steel quality. Beams can also be chosen differently, but I'm thinking of starting with the same material and finishing with the same material right now. While our brace rods on the side are at 70% capacity in this state, our columns are at 83% capacity. Let's take a look at the cost. I wonder if we chose something expensive. The section we will use in a 20-meter span is 26 kilos per square meter. Let's look at the shape of the building. Is there any place that bothers the eye? It would have been better if one more purlin or two more continued here. Maybe we could make it a little lighter then. 26 kilograms is pretty good for a building like this type structure, but let's try to get even lower, shall we? For this, I first increase the following from the model section. I increase tapered part lengths, for 4 purlins. I also want these not to be too high. I reduce them to 0.70 meters. We want reduce the beam sections. Is there anything thinner than 140 by 8 in inlet sections? 300 to 6 from such a slimmer profile. Columns and beams. Let's see from here. There is no problem in earthquake regulations. When we look at it, all frame elements cross sections are enough. Now the approximately cost analysis. 24 kilograms. By simply changing the sections. Let's look at the cross section of structure again. It turned into something like this. Now from here, we can actually access the diagrams of its frame elements. The schematic representation of the roof plan. The information of the columns and braces used. You can access the list of materials here. These are the things that show how much they've been used. There are nuts, bolts, anchors and stuff here. Now one of the missing analysis in this building is connection calculations. Now let's see what's the problem with that connection calculation. Connection analysis will be made for the following load combinations. The program says there is a problem with the moment resistance. What is the source of the problem? It's usually the thickness of that plate. Here, a 15 mm thick plate will be used. Let's see if there is anything bothering the eyes. I don't think so. We save this as XZ20R. Now I've moved to the RGHT side column of the building. Connection on the right. It will be something similar with left column connection. Let's look at the results. The connection attributes are correct, everything is sufficient. We looked at the connection itself, nothing bothering us. We can get two-dimensional connection detail drawings from here. These are dimensional controls on the thickness of the welds and plates. From here, we can go into the details of the calculation and see the detailed calculations about the connection detail here. How the calculation is done is explained in detail here. Between here, 2 beam splices left. Looking at the results, there is a problem with the plate thickness. I made this 15 just like the other one. It worked just fine that way. We can put one more bolt in the middle of the plate from here. Let's see. 58%. I wonder if it was enough when it was 10 millimeters? It could be done this way with 3 bolts. We saved this as 7R. There was a problem with the node 10. Let's see. There are 3 bolt rows, Let's apply the values we recorded as 7R for this as well. Our plate was 10. That's enough too. Now we come to pad foundation and base plate connection design. Let's see what the situation is with our base plate connection. There is a problem with the thickness of the plate and there is a problem with the reinforcements. We have to increase the plate thickness. First, let's enlarge the plate dimensions. Let's look at the base plate. I made it 330 by 500 and I made the plate thickness 20 mm. Seems to be enough at 90% capacities. I can put one more anchor rod in there. I put an anchor rod in that beam flange. Flag plates are a little too high. That's why I made the heights of these plates 150. It does not take these into account in the calculation, but I think it looks good for the rigid column base. We could remove them from here if we wanted, but I prefer their presence. Let's see how we are. All that's left is the reinforcements of the pad foundation. For the reinforcement of the pad foundations, we moved on to the foundation. Reinforcements are here. 10, 10, 10. We need to increase the longitudinal reinforcements a little bit. I made bar diameter 20 mm. It would be nice if I increased the traverse reinforcements a little bit. Let's draw it now. We're going to have one foundation like this. And the column will look like this. I saved this as 15R. We came to the next column base. I looked at the results, same as the other foundation. Let's refresh the drawing. Now let's see our structure in 3D. Now let's look at the 3D model of the building. Our program drew the connections, made the stability connections. It tied the rods. It drew the support of the purlins. It drew girts, column base plate and pad foundations. While drawing, the color difference indicates that they are different in thickness. What we're going to do next is numbering. In this state, it weighs 25 kilograms per square meter. Let's take a look at the actual cost here. The actual cost was 25.41 kilograms. There was a weight difference, not 24, it was 25. Now from here we go to the drawing list. Let's get the blueprints from the drawing list. I want to get this drawing together. The drawings have arrived. This is the column application plan. Here are the anchor numbers. On the side, this is anchor rod detail. There are base plate thicknesses and dimensions of the nuts and anchor rods informations to be used on it. There's the pad foundation application plan on the right side. It's got a front cross section over there. There is a left cross section at the top. This is the roof plan. The parts used in the roof plan have their names here. Here is information about their lengths. These are our plan drawings. Then cross-section drawings. That 2-to-2 axle is one of the calculated axles. Let's see in order. It draws cross-sections like this. Then it draws the distance between purlins. For example, reaction forces are required here. This is the model of our construction. These are the symbols of the reaction forces. Axial force, shear force, moment of the 15th point. Here are the reactions according to the load combinations. This is PEB type of structure. We need a plate list to cut these plates. 11 pieces of PEB B1. These are probably rafter single parts. 22 of these were to be cut. "11 of these will be cut. Other plates are also listed here. Some of them overlapped. These are our stiffener plates and column base that we use in connections and other plates. As for how to fit up them. For example, let's just see one beam and one column assembly part drawing over here. This is the assembly part we're talking about. This is the cross-section that will come at column beam connection. That's the other side connection cross-section. 3D drawing of this assembled part. It will be this way. One of these will be cut for this assembly part. This piece was already on the plate cut list. Then the lower and upper flange of this rafter. Other stiffener plates. These are the plates comes from the bolted connections. This assembly part can be obtained when the plate are cut and welded in this way. This is our C1 column assembly part. C1 columns described here as PEB C1, C1, C2, C3 single parts that needed for it. Those single parts will be cut. Those were the cuted by using CNC plasm. We made it on the other side just so that we can see what the dimensions are here. In this way, it prepares the assembly part drawing. Now let's come to the calculation reports. Let's get some of the calculation reports and see what we have. Let's take this from 2 axes. Let's even take all of them. It combines the necessary drawings and obtains reports from them. We will not keep the next examples that long. Since we have already shown the connection calculations here, there is no need to show the same steps in the others. In the following examples, we will only show the solution of the building. Here is the calculation report. It starts with the table of contents. Then it introduces the building. It shows the cladding loads and snow loads on it. We got a very low snow load in this building. These are calculation of wind loads. It is applying different loads like this. It made 4 different wind loadings such as left, front, right and back. According to these are assigned load values it made. Then it calculates the temperature differences according to EN January 5, 1991. It will calculate earthquake loads now. For earthquake loads, it calculated the period of this building as 0.806 s and distributed them as equivalent earthquake loads. Next comes the secondary member calculations. Here is the calculations of cold-formed purlins. Here is the calculation of cold-formed Girts. When it switched to the main carrier system, it said, "These are my load combinations." We calculate according to these load combinations. When calculating, it first gave the design result summary table. Then it checked the displacement in the columns and beams. These are limitations. It gave the information of the frame elements. Then it gave the cross-sections and steel grades on it. It gave information about the loads on it. Afterwards, it made earthquake regulation checks. Here it checked the relative story drift. Then it came to this H300 beam, it's checking the beams now. While doing this checks, it gave a result summary table. Apart from the summary table, this is how it shows the calculations in detail, so that the calculations can be checked. There was a problem with the displacement control over there. Even if it's something very small. Then comes the calculation of connections. Let's first examine this beam column bolted connection. It gives the sections used in the calculation. Then, load combinations. In this way, it gives detailed calculation reports. Then comes the pad foundation and base plate connection design. When it comes to pad foundation calculations, it calculates the soil bearing capacity according to Meyerhof formula. Here we enter to geotechnical engineering calculations. In this way, we have given detailed calculations by giving calculations of column base and pad foundations. There is also drawings so that their calculations are understandable. We thought it would be nice to have a drawing next to it. These are the appendices of the calculation reports. These are the appendices of the account reports. In A3 format. Our column and pad foundation application plans are like this. These are the placements of our roof braces. In this way, we finished the project after receiving the reports. Let's see the final version from here. This is the connection detail of column to beam. Let's see the final version from here. This is the PEB structure that we design. We save it as a project image here. Let's show Tekla export in the next video.